So the first limit that we are computing is the limit when x goes to plus infinity. So my variable x is a big number, is a large number, and it's going to infinity. And let's say that I want to compute the limit as x goes to infinity of x squared plus 2x plus 1 divided by 3x squared plus 4x plus 2. Does somebody know? In fact, somebody who is exercised to do that can find this limit in 1 sec. Maybe somebody of you know. All right, so the limit, so the larger number you choose, you will see that you will approach this number. So when x goes to infinity, meaning that way you choose a larger value for x, you will see, if you take your computer or a calculator, that this computation is going to approach 1 divided by 3. So why? Let me explain you why. So let's write here the fraction. So you all should know, I assume, that you can put x squared in front here. So if I take x squared, if I choose x squared in front of the numerator, I obtain 1 plus 2 divided by x plus 1 divided by x squared. And I can do the same thing for the denominator. So I put x squared in the front and I obtain 3 plus 4 divided by x plus 2 divided by x squared. Now, what's interesting is that, so in the numerator and the denominator, these two cancel. And so I'm looking at this quantity divided by this quantity. But if I take 2, if you have $2, but you have 1 million person, you're getting like nothing. Okay, so in fact, when x is going to plus infinity, you're taking a large number, this is converging to 0. And this also to 0. And this also to 0. And this also to 0. So what remains here is 1. Because 1 plus 0 plus 0 plus 0 equals 1. And 3 plus 0 plus 0 equals 3. So finally, this converges to 1 divided by 3 as x converges to plus infinity. And so what I've done here is quite general. When you have a polynomial, a fraction of polynomials, you can always do this thing to compute the limit at infinity. Is there any questions? No questions? Everybody is okay with that? So I suggest, but you're not, it's not mandatory, but I suggest try to choose another polynomials and try to compute the limit and do that as an assignment. So we are going to do 6 limits, okay? So another limit. All right, so this is actually easier. So if I want to compute the limit when x converges to 0 of x times cosine of x, so cosine of x is a periodic function which you can roughly represent by cos of 0 equals 1, and then it decreases and it goes like something like that, okay? And I'm looking at this quantity as x goes to 0. But in fact, here everything is well defined. So cos of 0 is 1, and for x equals 0, x equals 0, and 0 times 1 is 0, so this limit is 0, okay? There's no difficulty here. All right. Any questions with that? All right. So 3, this one is a little bit more difficult. It's related to the other one, but so limit when x goes to plus infinity of cosine of x divided by x. Does anyone have an idea? So let's look at this picture here. So this is the cosine. So the cosine is a periodic function that goes like that. So you go to infinity and it goes again and again, it's periodic. It oscillates between 1 and -1. But here, as x goes to infinity, this is becoming a very, very, very large number. So you have something that oscillates between -1 and 1. You know that -1 is less than cosine of x is less than 1. And you divide this quantity by large numbers. So at the end, you have that actually -1 divided by x is less than cos x divided by x is less than 1 divided by x. But this is going to 0 and this is going to 0. So this quantity has no choice. It is becoming smaller and smaller, so this limit is 0. All right. The two next ones are a little bit more difficult. There are some computations to do. But it's useful for the derivatives. Let's say that I want to compute the limit as x converges to 0 of the square root of 2 plus x minus square root of 2 divided by x. So if I look at the numerator, when x equals 0, this quantity is square root of 2, if I take out square root of 2 from square root of 2, I obtain 0, but on the denominator, I have also 0. I don't know what's going on. When I divide 0 by 0 as a limit, I can't say what's the result before. If I don't use a trick or something, I can't know. So we are going to use a trick to solve this limit, because as is, we don't know. But instead, I can use the fact that I can multiply here by this quantity. And so you know that when you have a plus b times a minus b, this is equal to a squared minus b squared. So that's what we have here. So here, the result of that is this square minus this square. So it is 2 plus x minus 2. So this is x, okay? So I can, so now if I do square root 2 plus x minus square root of 2 divided by x times square root 2 plus x plus square root of 2 divided by square root of 2 plus x plus square root of 2. What do I obtain? I obtain x divided by x times square root 2 plus x plus square root of 2. Now, as x goes to 0, so this actually x divided by x, I can simplify. And as x goes to 0, this is going to 1 divided by 2 square root of 2. Is that okay? So, can you do the same computation when, let's say, a is a positive number? Can you compute, by analogy with what I've just done, the limit as x goes to 0 of square root of a plus x minus square root of a divided by x? I'll let you 5 minutes to think about that. So this is the result. So how do we obtain it? I just will develop this thing. So it's a squared plus 2ax plus x squared minus a squared. So now if I take a plus x squared minus a squared divided by x, I obtain 2a plus x, which converges to 2a as x goes to 0. Great. So the last limit, and this one is really tricky. Let's try to look at the limit as, let's say, x go to 0 by positive values of sine of 1 divided by x. So can you figure out what's going on as x goes to 0 plus in this expression? So first of all, so when I have a function, when I have two functions, f of g of x, let's say, and if I look at the limit when x goes to 0 plus of f of g of x, I will look at the limit of g of x, and then if it's okay, I look at f of g of x. So in this case, if I look at the limit when x goes to 0 plus of 1 divided by x, this is plus infinity. But the sign is oscillating between -1 and 1. So this is a little tricky. So this function is not defined at 0, but actually it will do something like that. And is going on oscillating again and again, infinitely, never reaching 0. So you have this kind of picture. So you don't have a limit here when x equals to 0. So think about it. So this one, actually, you cannot compute a limit. There's no limit. It's not even plus infinity or minus infinity. When you approach 0, you're still oscillating between -1 and 1. All right. So that was it for the assignment, discussion about the assignment. So there's an assignment due for next week. You just have to compute some limits, 5 to 10, and it will be okay. And you have to put a file on. I sent you the information, right? Okay, so now let's start the discussion about the chapter 2. And it's derivatives. Oh, there's no need for my camera to be on. So we will see. Let's do some preliminary remarks. So this will be preliminary. So this will be short. So when you talk about derivatives, in fact, there's a limit process involved. And so it's very useful to describe law of physics, laws of in biology, for example, a bacteria, laws of financial markets. So yeah, derivatives are everywhere to describe natural phenomena. So that being said, let's do some more concrete things. So usually we introduce limits in the following way. So So let's choose two ways. The first is by tangents. Let's say I have a function here. I draw a function here. I draw a function, let's say between 2 points A and B. So I have, so here it's f of A, and here is f of B. So since I have 2 points, I can draw a line that connects these 2 points. And so what's the slope of this line? So the slope of this line is f of B minus f of A divided by B minus A. So it's basically says you what's the speed, what's the intensity. So how much are you growing when you increase in the x-axis? How much do you increase in the y-axis? But I could choose another B. So let's say I choose B2 here, and now instead of the yellow line, I obtain a green line, which will connect the points AF of A and B2F of B2. So something like that. So the new slope for the green line is FB2 minus F of A divided by B2 minus A. So I could choose a B3 here and then a B4, and let's say a sequence Bn that's converging towards A. And I could look at the sequence FBn minus F of A divided by Bn minus A. And if in fact, at the limit, what do I obtain? I obtain the slope. If my point here, my point A is here, I obtain the slope of what we call the tangent, which is a line that touch, in my specific case, but this is the idea. My tangent touches the curve here in one point only, which is in AF of A. So the slope here is a limit this is the slope of the tangent. I can write also it as FA. I can write also this slope of the tangent as the limit as h goes to 0 of FA plus h minus f of A divided by h. And in fact, this slope of the tangent, we can write it f prime of A. Okay, so the derivative, in fact, of f at the point A is defined by this limit. So this is a big idea of calculus A. It's one of the big ideas. Right, so another way to introduce derivatives is by speed. it's a classical example, speed of your car. So if you are driving your car between a point A and a point B, so you can compute the distance traveled from, so the distance at point B, if B is a city, for example, and A is another city, but it's better to say, let's do it better. So if at a time T1 you were at some place, and next at a time T2 you are at another place, you can say that between time T1 and T2 you have traveled f of T2 minus f of T1. Okay, if you have if your f measures your position on some line. Okay, and now if I divide by the time, this gives you the average speed. Okay, so ft2 minus ft1 divided by t2 minus t1 is your average speed. So you went from New York City to the beach, and there was 15 miles in, I don't know, half an hour. So you have an average speed. Now, if my T2 converges to T1, so if I look at limit as h converges to 0 of ft plus h minus f of t divided by h, this is the speed that is indicated in your car. So this is the instantaneous speed. And again, this is a limit. And this is a derivative. So when you drive your car and you look at your speed, this is the instantaneous speed, and it's a limit. All right. So another and the last example for derivatives is, for example, the growth rates. In labs, they can, for example, observe the length or the area of some bacteria, and they come at day one. It's like that. And then day two, it's like that. And day three, it's like that. And so it's the same. You have, for example, the average growth between day 2 and D1. But if you want an instantaneous growth rate, you will have to take the derivative. So again, you have an expression like limit as h goes to 0 of ft plus h minus f of t divided by h. All right. So for a function f, we say that when this limit exists, so the derivative of the function f at a point x is defined by the limit as h goes to 0 of fx plus h minus f of x divided by h. So I gave you 3 examples to think about it: tangents, speed, and growth rate. But the mathematical definition is this one. And you can see, so at the beginning, I mean, half an hour ago, we computed, for example, square roots of, it was, the notations were a little bit different, but that's not meaningful. So we computed, for example, this thing for a positive number x. If I divide it by h, we saw that this is converging as h goes to 0 toward 1 divided by 2 square roots of x. So what you have is that the derivative of square root of x is 1 divided by 2 square root of x. We did it as an exercise on limits. And we also saw that the derivative of x squared is 2x, because we computed x plus h minus x squared divided by h, and we saw that this is converging toward 2 times x. So we can see that for some functions, we can compute the derivatives and we obtain another functions. And in fact, let's n be any positive natural number. We can also compute the derivative of x to the power n. So this will be the last exercise for today. I want to compute the derivative of this function. So to do that, I will need to compute this limit, x plus h to the power n minus x to the power n divided by h. So I don't know, there's some trick, but I'm also here to give you some tricks. That's also the idea of this course. So now this can be 1 million, this can be 3, this can be 4. So there's a formula for that. Maybe you know, maybe you don't know, I don't know. So x plus h to the power n, I can write it as the sum from k going to 0 till n. So see, the n here is the same as the n here. I just need to introduce a new variable for illustrating my computation. And I could write it in different way. So I write it here. This is a number, CKN. This is a number that you learn when you do combinatory stuff in probability. So this is a number, and I don't need all the numbers, so I will not explain that in detail. I just explain what I need exactly. And so I will write it as h to the power k times x to the power n minus k. Okay. So now, if you look at k equals 0, I know that C0n, this is 1. And C1n, this is n. Okay? So now let's write something more here. If I write x plus h, h plus n minus x n, I'm going to first write the first terms. So C0n is 1. So the first term is x to the power n. The second term is n h x n minus 1. And then plus the sum from k equals to 2, because I wrote all for k equals 0 and k equals 1, I already wrote it to n of ck n hk x n minus k. Those are, again, are positive numbers. I don't care here about the exact value. We can discuss that another time if you want. Okay, and if I take out the xn, this cancels. And if I divide it by h, I obtain, so what do I obtain? If I divide by h, I obtain n, oops, sorry. I obtain n x n minus 1 plus the sum from k equals 2 to n of ckn. So before it was hk, but now I have divided by the h, so it's hk minus 1 and x n minus k. All right, but well, now when h goes to 0, all these terms have some power of h. So for k equals 2, h equals 1. So when h goes to 0, this goes to 0. And in fact, everything goes to 0. So this goes to 0. And the only term that remains is n x n minus 1. So finally, we got that if the derivative of x to the power n is n x to the power n minus 1. So doing that, the derivative has been computed for a lot of functions. So you have a lot of known function derivatives. So I will give you that as some material. And I will also post an assignment to be done in 2 weeks. And that's it for today. If you have questions, I will be happy to answer.